tsunami could really whack most of the satellites in orbit. Just at a go, wipe out our satellite industry, which would take out communication and weather, and not to mention imaging and all the military and the Earth climate satellites and all of that stuff. One of the Mars probes was lost to a solar flare. The Beagle probe, ESA. ESA has had terrible luck getting to Mars. Just terrible. There it is. When does standard time begin?
In Arkansas, daylight saving time in the United States started around Sunday, March.
Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explore Alliance, and this is the 37th episode of How Do You Know with Dr. Daniel Barth. This time, Daniel goes into explaining what happens when you get solar prominences and flares and mass coronal ejections and even solar tsunamis. So, Daniel, it's great to have you on the show again. Yep. And it's, you know, the little video that we just showed about, you know, understanding the universe through spectra kind of really does start off with taking spectra of the sun.
It did.
Right.
It did.
And
that's right.
So we have several people.
Yeah, Fraunhofer and Kirchhoff, two German scientists, and Fraunhofer is also famous for inventing the German equatorial mount. And
That's right.
That's right. And Fraunhofer, Kirchhoff originally discovered lines in the absorption lines in the solar spectra, and Fraunhofer went ahead and said, no, there's not 7 or 8, there are hundreds and hundreds. And it was he and Bunsen of the Bunsen burner fame, who did a lot of the early spectroscopy work. And what they would do is they would take a spectroscope, a fairly crude device by today's standards. It was a small brass telescope that was bent, and it had a prism in the middle of it. And by changing the angle respective of one telescope tube to the other, they could look at a very small part of the spectra. And they found that when they burned things like calcium metal or sodium salts or potassium, copper, these sorts of things, that they would get very definite colors. And they found that, each element has a fingerprint on the spectrum. And so they realized quite early on that, gee, what's happening here with the sun is there are elements in ionized form in the sun's atmosphere. The light is shining through, and these elements absorb the same colors that they emit when they're hot. And so they would leave these dark lines. Well, they went ahead and tested all the known elements and charted out their spectra. And they would go ahead and they were basically, okay, we know these two, everyone's familiar with the two bright yellow lines of sodium, and mercury vapor gives us the bright green line and some blue and other things, and the hydrogen alpha spectrum in red, et cetera, et cetera. And they got done and they realized, there are more lines here than we have elements to account for them. And they realized there must be a unique element on the sun, which they named helium after Helios, the god of the sun. And it was the only element that wasn't discovered on Earth. It was discovered on the sun first. Later found in reservoirs in the ground from the decay product of uranium. But this, I looked it up just for fun, and Google erroneously claims that Isaac Newton invented spectroscopy. He did not. He indeed, I was the first one to classify the 7 colors, the 7 standard colors of the rainbow, and he split blue and indigo apart because he believed that 7 was a significant number, and so he decreed there would be 7, the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And we talk about the Lyman series and the Pasha series, and all these series of various hydrogen series. And it depends on how the atom is excited. And there's a whole science to this, and it's quite wonderful. And that's where Webb is going, because Webb uses infrared spectroscopy. And why infrared? And we talked about this, Scott, because you can see through dusty areas with infrared that you cannot with visible or ultraviolet light. And so exciting stuff coming up.
It is. It really is.
It is.
Well, that's great. So what, I've never heard of a solar tsunami. So I expect that you'll be getting to that, but
that's a catchy phrase that some of the science news websites are using now.
Okay. All right.
And it's not a technical term. It's a popularizing science term. But a couple of other things, and I thought maybe we'd try something this week, Scott. There's so much news coming out of astronomy and space science every week, and I thought maybe if we take 5 minutes and just touch on a couple of topics, something that we wouldn't necessarily do a whole show on, but we have daylight savings time today. Hooray, boo, however you feel about that. I'm personally a no fellow on that. The pollsters indicate that a majority of Americans, like 65 or 70%, really hate changing their clocks and wish we would just stop with this stuff. And there was a lot of reasons for it. We changed the clocks because it keeps the hours of daylight reasonable. It keeps solar noon closer to actual noon and all that sort of thing. And for a long time, the justification for it was that with businesses, if you have more daylight during the summer hours, you will get more trade. And so there was economic justifications for it. And given our online propensities today, the reasons just don't really exist anymore. It's one of those things that we keep doing because we've always done. It's the old story about hold a stick up and the first sheep will jump over it, take the stick away, and all the rest of the sheep will continue to jump in the same spot. So it's an interesting thing. I remember, probably you do too, when you were a boy. Do you remember the year when Nixon said, no, we will be on daylight savings time the whole year in order to save energy?
I do not remember that. Did that actually happen?
That did actually happen, and that was in the early 70s. And the interesting thing about leaving your clock set ahead, when you get into the fall, you get to where the sun doesn't rise until 9 or 10 a.m. It's like living in the Arctic. And I remember that in the winter, we were going to school in the dark and the sun would rise sometime before lunch. And parents and kids universally scorned it. And so we went back to standard time in the winter. But we've just jumped to daylight savings time. And of course, everybody knows that first Monday is terrible because you get up an hour, you lose an hour of sleep and get up an hour.
Oh, yeah, that's right.
The other interesting thing coming out is there's a study coming out of university. I think it's one of the British universities. And it's talking about how do early galaxies form? And we see, and we're going to see more with Webb, because Webb can see farther back in time than we can with other telescopes. And one of the questions is, how did we form galaxies? Galaxies seem to appear almost as soon as stars do. And shouldn't galaxies take like 500 million or 1 billion years to form after stars start to appear? And there's some indication now that supermassive black holes may have formed before most stars, and that the universe experienced a phase change from hot and dense to cool and low density. And the idea is at a certain point, the universe might have been hot enough, dense enough, that dark matter actually collapsed to form supermassive black holes in a phase transition. And it's brand new. It's quite speculative, but it's coming like, if there was this phase change, and we know about phase change, right? We had the snow last weekend that it lasted for about a day and it changed phase, melted away into liquid water, and it was gone. We see boiling water change from liquid to vapor. And so we have this phase change situation. And there's some thought that a lot of our dark matter, and people say, well, there's so much of the universe, 85%, 84% is supposed to be dark matter. Why doesn't it form black holes? Well, it doesn't interact with itself or ordinary matter very well. But the theory is now that in the early universe, conditions may have just been right, dense enough, compact enough, that you had this phase change and a great deal of dark matter formed supermassive black holes, which would, of course, seed and speed up the formation of galaxies. These supermassive black holes would gather star-forming material, which means stars would form faster and they would form in the spiral patterns we now know for large galaxies. So kind of some interesting stuff coming up in the news, and we hope maybe we'll do some more programs on these things. And if you're interested in any of these topics and would like to see a How Do You Know program, I hope you'll comment in the comments because we love to be viewer driven here.
Yeah.
Anyway, let's go ahead and talk about solar tsunami. And I'm going to share my screen of notes with our viewers. And of course, Scott always posts my show notes for people. And the show notes include quite a number of links on the internet to help you learn more and explore and learn a little bit. But let's just talk about events on the sun's surface. And we're kind of going to go from the wee, small, insignificant events to the large and spectacular. But when we talk about the sun, planets don't compare to stars. Our sun is not a particularly spectacular star. It's a yellow class G dwarf star. It's relatively small. It's relatively mild. It's quite well behaved. It doesn't have huge eruptions and violent pulsations, and it's not a variable. All these things that we think would make life very, very difficult. Thank you very much. Places like red dwarfs, which, we could have planets in the habitable zone quite close, but then the solar flares and prominences from red dwarfs could be just extraordinarily violent at those distances. So we look at our sun, which is kind of a wee little star, but you talk about comparison to Jupiter and to the Earth. It's about 100 Earth diameters wide. It's about 1 million kilometers across, where the Earth is on the order of 10,000 kilometers across. So the sun is about 100 Earth diameters, which you think about, wow, and that's really crazy. And the volume of the sun, the mass of it, all of the planets together with Jupiter amount to a tiny fraction of the sun's mass. There's nothing on Earth like a star. We're 100 million miles away, 150 million kilometers away. And even at that distance, the sun delivers 1 watt per square meter to the Earth's surface and the moon's surface as well. The moon gets just as much sunlight as we do. And you think about, wow, 1 watt per square meter. And how many watts does it take to run a home, and how many watt hours of energy? And you realize the amount of solar insolation or solar radiation striking the Earth is just, it's tremendous. Had we the ability to capture it in a really efficient and broad area, we wouldn't have to worry about oil and who has it. We would all be driving electric vehicles.
Right.
But
right.
This idea of how efficiently can we capture solar energy is difficult. Ultimately, all the energy we capture is solar. Petroleum comes from plants which capture solar energy. Wind power comes from movement of air, which is driven by temperature differentials, which is solar power. And we talk about hydrodynamic power, and the water cycle is again driven by the power of the sun. So ultimately, all our power sources are solar power. It's just most of them are mediated through several steps removed from direct solar energy. And the teeniest weensy little magnetic disturbance we have on the solar surface, Scott, is a sunspot, of course. And people see them as dark. And why are they dark? Because they're cooler. They're about 1,500 degrees cooler. And it's simply not that sunspots aren't bright or don't give off energy. It's just that sunspots give off a lot less. It's like someone lights a birthday candle, and you're looking at the birthday candle, and then a few feet behind the birthday candle, somebody turns on an automobile headlight. Well, the light of the candle is absolutely lost in the glare from the headlamp. And it's the same thing with sunspots. They're giving off light. It's just so much less and so much cooler than the rest of the surface that they appear darker. And these areas are actually magnetic in nature, where you have lines of magnetic force that are compressed, and this allows energy to flow out and dissipate. That cools the solar surface and makes a sunspot. But it also is a place where magnetic lines are concentrated together. The sun is not a smooth environment. It's a very turbulent environment. The sun is rotating. There's differential rotation. We're not used to that idea on Earth because planets like the Earth, Venus, Mercury, Mars, and our moon, they have a singular rotation rate. The Earth rotates once every 24 hours. The moon rotates about once every 705 hours. And since these are rocky terrestrial class bodies, they all rotate of a piece. And it's a good thing they do. If the Earth had differential rotation, as Jupiter and Saturn do, where the poles are rotating more slowly than the equator, on these planets, there's shear, there's slippage because different belts rotate at different speeds. If the Earth had that sort of phenomenon, we would be dragging pieces of continent, would be slipping past each other. The friction would cause not only tremendous seismic damage, but a lot of friction, a lot of heat. The surface would melt. Differential rotation for a terrestrial planet would be terrible. For the sun, however, this differential rotation serves to twist the magnetic lines of force, and the sun's magnetosphere gets twisted like a giant spring system, and it stores unbelievable amounts of energy. And it turns out that these lines, every once in a while, the stress gets too great and they snap back. We've all played with magnets, and you can take two magnets and switch them to repel, and one pushes the other across the desk, but then you reach a tipping point where the other magnet flips over and snaps too. All children have played with magnets this way. Well, the magnetic field lines of the sun do much the same thing. And when these lines snap, they release tremendous amounts of energy. And so we get a solar prominence, sometimes called a solar filament. And these are great loops of plasma. I think Star Trek Voyager had an opening sequence where the ship flies through the loop of a solar prominence. It's just a very cool special effect. You remember that one?
Yeah.
And you see on the little diagram there, you see how big Earth is compared to this tremendous loop of plasma. And this plasma, Scott, is a stream of charged particles. It's very much like a lightning bolt. When you have a lightning bolt through the air, that amount of energy ionizes. All these particles, the oxygen, the nitrogen, the argon, all the various gases get ionized, and they get heated very hot, and then they release their energy as they collapse back to their ordinary state. This is how a fluorescent light bulb works. If you have compact fluorescent in your home, this is how they work. The atoms are excited, and then when they collapse, the electrons collapse back to the ground state, they give off energy as light. Well, the sun is virtually entirely made of plasma. And so you get this, this tremendous loop of hot ionized material. And the solar prominence, yes, has a lot of energy. One solar prominence has more energy than we have released as human beings in our entire history. Tremendous amount of energy. And but it's bound, it's completely locked to the surface of the sun. They're loop forms because magnetic fields form loops. You ever done that experiment, Scott, where you put a magnet under a piece of paper and sprinkle iron filings? Have you ever done that?
Sure.
Sure. I'm
I used
sure
to have
lots
a toy puzzle that was
of course.
and it was like a figure of a man, and you would put a beard on it.
Yes.
I remember the kind of
and
patterns that it would make, you know.
Yes, you could take the
iron
little magnetic
filings.
wand and drag iron filings along and give him a beard or hair or whatever.
Right.
Yes, I could never get it to look like anything except blobs of.
It always looked
But
bizarre.
yeah, you could do that, and we see with ferromagnetic fluids, and there's various science demonstrations. But the classic one is here's a magnet under a piece of paper and sprinkle iron filings, and you can see that the magnetic field forms loops at the end of a bar magnet. This is very much what's going on with a solar prominence. You get these magnetic fields, and the charged particles are bound to these loops. They cannot escape these loops. They're not energetic enough. And so we get these lovely, lovely, beautiful things. Those of us who have access to a solar telescope with a hydrogen alpha filter. The interesting thing is these are mostly giving off light in the H alpha spectrum, which is not very bright compared to the visible output, visible light output of the sun. So we need very special filters. And I'm just going to say it. I know most of our viewers are sophisticated about these things, but friends and neighbors, do not point a telescope, binocular, camera, or any other optical instrument at the sun unless you have proper filters and you purchase your filters from a proper retailer. We went through the last time there was a big solar eclipse. We went through sorting because, of course, the scammers come out and they were selling scam solar eclipse glasses, which really didn't protect people from the sun. Remember that?
Some of them, oh my God, you could just hold them up in a regular room, without strong lighting and see across the room with them. So
exactly. And so
others were better than that, but not a lot better. You could still see through so it is very, very important that you protect your eyesight, especially when you're looking at the sun.
A real solar filter is going to block out, you're only going to pass about 1/10,000th of the light through. And this is either a glass or a Mylar aluminized solar filter. It always goes on the objective end of the telescope or binocular. It goes on the far end, not where you look through. They used to sell solar filters that would screw into the eyepiece. Do you remember those?
Yes.
And those are terrible.
They're illegal in many states.
Yes, if you have one, the proper procedure is to hit it with a hammer and then throw it away.
Yes.
Because if you have a telescope, all the heat energy would be focused on this piece of glass. And if it fails due to heat stress, then the damage to your eye is instantaneous and irreversible. So yes, we're just going to give the sun warning. If you're going to observe the sun, it's very exciting, lots of fun, very informative. But for heaven's sakes, you need to have a proper solar filter purchased from a reputable dealer like Explore Scientific or another reputable company. Don't just go and buy Bob's Pretty Good Solar Filter, or I found this deal on eBay. Look how much cheaper it is. You only have two eyes and they're not replaceable. There are no bionic replacements. So
Not yet.
Not yet. And the same thing goes with a camera. A lot of times when I sold telescopes, we would get people during eclipse time and they would come back in, well, I used a solar filter for my telescope, but now my finder scope won't work. And the finder scope, the reticle, of course, was right at the focal plane, and they were burning the reticles, the little crosshairs out of the finder scopes. So after eclipse season, we would make quite a bit of money fixing people's finder scopes, putting new reticles in for them. Anyway, let's talk about a solar flare. If the release of energy is powerful enough that the magnetic field cannot contain it, and the stream of charged particles actually is released by the sun. And this is different from what we call a solar wind. The sun is always emitting charged particles. Helium, neon, argon, oxygen, carbon, mostly hydrogen and helium make up the solar wind, protons and what we call alpha particles, but there's lots of other things. The solar wind is given off all the time. Solar flare is different. This is a tremendous explosion, a lot of plasma, billions of tons of plasma. And they're releasing energy that's too big to be confined to the loop of the magnetic field like the prominences. And these two are associated with sunspots. Solar flares tend to erupt from sunspots. Interestingly, we find that most of the time we see solar flares are when the sun is in its active cycle. There's, of course, the 11-year cycle where we hit solar maximum, the greatest solar activity, the most number of sunspots and solar flares. And then we have solar minimum, and these things are an 11-year cycle that's been known for hundreds of years. But the solar flares, these can last from a few minutes to several hours. And these magnetic storms, if you will, release energy across the whole electromagnetic spectrum, everything from long radio waves to intense X and gamma radiation. Lots of stuff in the AM and FM band, and there a lot of stuff in the hydrogen alpha band. These things also accelerate charged particles. So it's like a huge particle accelerator. It's like a big cyclotron. Picture the CERN cyclotron and scale it up by about 1 billion. It's releasing such a tremendous beam of energy. These solar flares release, a few 100,000 gigatons of energy.
Jeez.
So you have megatons, right? You have megaton weapons, and the biggest weapon anybody has ever built. It was crazy. It was the, I believe it was the Tsar Bomba. The Russians built one that came out at about 50 megatons, and they dropped it on an island, which isn't there anymore.
Vaporized. Yeah.
The Ivy Mike experiment that the Americans did was a 15 megaton bomb, and the coral atoll it was detonated on isn't there anymore. You're talking a bomb big enough to destroy metropolitan New York, Moscow, Tokyo. It's just a hideous amount of energy. And now we're going scale up by 1,000 and go from megaton to gigaton. So it takes 1,000 megatons to make a gigaton. So the biggest weapon we've ever built as human beings is 50 mega, and it would take 20 of those to make a gigaton. And you're talking a few 100,000 gigatons of energy. It's just a stupid amount of energy. It's compared to our paltry energy usage and energy generation of all sources, from military, commercial, lighting a match, burning petrochemicals, all of that. It's not even, if you in the scale of things, it's not even there. Like I said, a solar flare releases more energy than humanity has produced in its entire lifetime. And I'm talking biological energy and all sorts of fuels and everything we've ever done. We're not there. 10 to the 22nd ergs per second. Most people aren't familiar with ergs. That's a physics unit of energy. But it's such a bizarre amount of energy that it takes scientific notation to even make sense of it. But even these are generally not powerful enough to reach beyond the sun's corona. They do sometimes. Solar flares do sometimes. And we find out that these solar flares, we have classes for them. And so I was looking up the origin of the notation, and it's kind of like the classifications for stars, O, B, A, F, G, K, and M. And you're like, what the heck were you guys thinking? Couldn't you have done A, B, C, D, E, F? Or alpha, beta, gamma, delta? But apparently not. But this is a logarithmic scale. Most people, Scott, are familiar with logarithmic scales only when we talk about earthquakes, right? The Richter scale and the modified Richter scale. So essentially, each scale is 10 times bigger than the last one. And within each scale, we rank them as 1 to 9. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1. But it's logarithmic, it's not decimal. So when we go B and C class, these are weak, little paltry, only a couple 100,000 gigatons of energy. And they're generally so wimpy that they really don't affect Earth significantly. A B event is of interest to astronomers, but it produces no noticeable space weather. And yes, friends, space weather is a thing. The sun is always producing solar wind, and then there's solar flares and releases of plasma and other things like that. So what the space weather is. Why do we care? Because we love our cell phones. Yeah, there's mine, my little cell phone, and we love our satellite data systems, which gives us imagery and weather and news and military technology information and all these things. Satellite communication, data exchange. It was funny. I was talking to a friend who was communicating by text with someone who lives in Russia. And I was thinking of my own circumstances where I send an email through the intranet. It's through the university system to a university student. And I have a student sitting at my desk and I'll say, okay, I'm going to email you an invitation to look at this document or whatever. And it takes 20, 30 seconds to get through. And I asked my friend, I'm like, wow, texting and stuff with Russia, your friend in Russia must take a long time. He said, no, it's basically instantaneous because I'm going over the intranet through landlines and stuff like that and modems, and he's going through a satellite system, which is almost instantaneous. But these satellite systems, the microwave system that our cell phones communicate on, these can be affected by solar flares. And certainly satellites in orbit, not to mention any astronauts that are working in orbit. And these sorts of radiation storms are no respecters of, gender, class, or nationality. And because the only thing that protects you from radiation really is a fair big amount of mass. You and I, Scott, are old enough to remember duck and cover drills. Remember that? Civil defense
absolutely.
Drills? Oh, absolutely.
Yeah. We had like real iron curtains. Okay. That
we did.
But yeah, or lead, maybe they were lead curtains. I can't remember, but they were.
Yes, lead line curtains. Yeah.
They were like blackout. Okay.
Right. And most people are
very heavy and they would pull, you would pull
the curtain,
across.
Right?
You got picked to do that job.
Only most people are familiar with lead lined fabrics now. Only at the dentist's office, they put the lead apron over you when they take an X-ray. But we used to have these in schools and office buildings and stuff, friends. Yep. And school children, we had to duck under our desk and hold the legs of the desk so it would protect us. And the joke was, tuck your head between your knees and kiss your bottom goodbye.
Right.
It's a civil defense drill. Well, we talk about these things, and the civil defense thing always said, oh, if there's an atomic attack, seek to go down into the ground because you need to put mass between you and a radiation source, right? So if a bomb goes off and the radiation particles are reaching you, the more material between you and the flashpoint, the safer you will be. Well, for our friends who work in space, it's really not practical to send up lead shielding into space because every kilo counts and costs. It used to be, what, $10,000 a kilogram to put something into orbit? I don't know if it's gotten cheaper or not. But
I would think it might have, but
it might
maybe
have.
it's still 10,000, but
10,000 today
maybe
is what 10,000 was 25 or 30 years ago.
25 years ago, exactly.
But you talk about putting lead, or in some cases they talk about, if you have a water tank, hide behind the water tank because water is very dense and massive. But you know what? Any kind of a radiation pulse like this, astronauts are at risk. Astronauts are absolutely at risk. For our satellites, the problem with a large dose of ionizing radiation is that it disrupts integrated circuits. It scrambles memory chips, right? The ionizing radiation is strong enough to disrupt the magnetic domains on a memory storage system. And so it scrambles the memory. So maybe the computer works, but the software has been fried out of it. So these radiation storms are very problematic. And not just that, but when we have a big surge of radiation into the exosphere, the outermost area of our atmosphere, and we're talking 50, 60 miles up, what happens is that exosphere heats up like the solar corona does, and it expands by tens of kilometers. SpaceX just recently lost a whole flight of about 40 satellites. They were doing one of their many satellite launches. And we had a solar flare, and it expanded the exosphere, created so much drag that they lost more than 40 satellites, which burned up and deorbited before they could get boosted up to a higher safe orbit, completely out of the Earth's atmosphere. And so these kind of things for B isn't much of a problem. C can be a problem. But then we have M-class. M-class, these cause radio blackouts in the polar areas. Earth's magnetic field loops like a bar magnet, and the places where the loops converge, where the field lines converge on the Earth's surface, is where the geomagnetic poles are. Not the same place as the geographical pole. The Earth's magnetic pole, the North Pole, somewhere in Canada, I don't know where or how many kilometers it is, and it moves and it wobbles and it changes from year to year. But these magnetic field lines capture these charged particles and funnel them down into the Earth. And this is what causes our Aurora Borealis. And with an M-class, you can get enough radiation, enough charged particles streaming down into the Earth's atmosphere. And all of these particles, as they enter the Earth's atmosphere, they are traveling along the magnetic field lines, and they cause radio noise. And the radio noise is very loud, random, static across frequencies. And so you can't get radio communication. Cell phone radio communication gets blacked out. Again, auroral displays in the polar regions. Yes, we have them. Yes, they're beautiful. And we've been having a lot of auroral displays in the last year or two. We are near our solar maximum. So we've been getting these lovely displays, and people travel up just to see them. I have a good friend who lives in Alaska, and he says, yeah, part of the reason he lives up there is he gets to observe the aurora. In 2007, I believe, they observed a flare that was so enormously large that it was off the scale. And so they invented the X-class. The X-class, there's no class beyond X. Maybe there should be, but, and you figure each time you go up a level, you go up by a power of, you go up and double the power. Well, there's no upper limit to X-class. And the largest recorded so far is X17, which sounds like a science fiction thing, doesn't it? The X17 class solar flare. These X-class flares affect the Earth worldwide. They overwhelm our magnetosphere so much. When this much energy plows into the magnetic field, the Earth's magnetic field actually pulsates the way a speaker does. And it's not unlike the way a ferromagnetic speaker and coil work. We send electromagnetic energy, and it causes the vibrations, and those drive the physical speaker cone. And our earbuds transmit us the podcast or music that we want to hear. This causes the entire Earth's magnetosphere to vibrate. When that happens, the exosphere heats up. But anytime, if you know, I know you know a bit about this, but in basic physics, anytime we have either a moving magnetic field or we have a charged particle moving in a stationary magnetic field, this is how electric motors and generators work.
Right.
When we have a moving magnetic field and a magnet, we cause force, and that's a motor, an electric motor. When we move the magnets through the electric field, then we have a generator. And essentially, these X-class can cause the magnetosphere to vibrate so violently that every wire becomes a magnetic or an electromagnetic inductor, and it generates current. The longer the wire, the larger the gauge, the more magnetic field lines cross it, the more electric current you generate. And so when you're talking about these sorts of things, these radiation surges and the magnetic pulsations, they can create electric surges inside electric equipment, even stuff that's not connected to a power supply. There can be enough magnetic oscillation that these wires basically induce electricity, and this kind of thing can fry circuitry. And not just in space either. A large solar flare that hit Earth directly could damage computer equipment. It's unclear whether it would damage, memory stick stuff that wasn't plugged into a computer. Would my USB memory be damaged? Hard to tell. Hard to tell. But anytime you have a vibrating magnetic field, well, what happens if you have a hard drive and you rub a magnet over it? You can erase all the information. Well, all you're doing is moving a magnetic field over the medium of the hard drive, right? So if the magnetic field of the Earth is moving strongly enough, you can, it would play merry hell with all of our storage and data systems. We think we have access to everything on the internet. But what if we had a huge solar event and all of that memory or much of that memory was erased? Yikes. Equipment was damaged and our ability to access what was left was erased. And our systems are not hardened against this. They are not hardened. One of the greatest vulnerabilities, Scott, is our electric power grid.
Right. Thousands
of kilometers of wire in a spider web all over the surface of the Earth. And a large solar magnetic storm could cause inductions, which could black out power for hundreds of thousands of people. And the electric surges. Before? Sorry?
Has that happened before?
We've had events that big before, but not in the modern era. Okay. There was a very, very big event in 1859, another one in 1903, but we didn't have the kind of power grid we have today. Even larger, the coronal mass ejection. Sometimes the sun has such a tremendous explosion that many billions of tons of material are actually blasted out of the corona. This is not a focused event like a jet, like a solar flare. This is like a grenade. It's a big field of material and it expands as it goes out. Solar flares stay relatively focused. Coronal mass ejections do not. The Carrington Event. 1st of September, 1859. A couple of astronomers in Britain, Richard Carrington, Richard Hodgson, observed this solar event. And it was sometime later, it takes a while for that pulse of plasma to travel the 150 million kilometers to Earth. It collided with the Earth's magnetosphere. They had auroras at the equator.
Wow.
You think about that. There were aurora observed in Cuba, Hawaii, Colombia, southern Japan.
Crazy.
In the northeastern US, people reported that the aurora was bright enough to read a newspaper by. And this is in an era pretty much without street lighting, right? 1859. The telegraph system was active at that time. And people reported because of the huge induction, telegraph operators, some of them were electrocuted. The sparking and discharge was starting fires at telegraph stations. There were telegraph operators who reported that there was enough electric energy in the wires for them to keep sending messages for hours without hooking it up to any kind of a power supply.
Oh, jeez.
So you realize, oh, this is powering the telegraph system for hours and with no power supply. You think about what would happen today with a modern Carrington event. No cell phone service. Not only your cell phone would probably be fried, but the whole cell phone transmitting system. Cell phone signals are in the microwave range. that stuff, that goes down. Radio communication, if you say, oh, well, I'll go old fashioned, I'll tune in on FM or AM radio. No, you're not going to get anything. The vibrating magnetic field and the particles traveling through the atmosphere would release so much radio static. There would be no communication there at all. Satellites, probably a Carrington style event would wipe out most of the satellites we have in orbit. There may be some military satellites, which you and I don't know about, Scott. I'm not on that mailing list. Maybe you are.
No.
No? Yeah, me neither. There may be some that are radiation hardened. But again, it's kind of like, well, what does it mean to be radiation hardened? We think of the Fukushima nuclear plant, which was designed to withstand a Richter scale 8 quake, right? And what did they get? They got a class 9 earthquake that destroyed it and created the huge tsunami in Fukushima. And so when you talk about, oh, this is a bomb-proof shelter. Yeah, really? It's like saying, oh, I have a bulletproof vest. Well, sort of, you know, but all of these things have their limits. And if you have a bulletproof vest, I hate to tell you, but there are people who have bullets who will tear through it. And if you have a bomb-proof shelter, well, there are bombs that will destroy it. If you have a radiation-hardened satellite, nothing is a match for the sun. The power of the sun is beyond it. And so we think about this and we go, wow, these solar tsunamis, these like the Carrington event, and have they happened before? And how could we tell? Would this leave any sort of a trace on Earth? And it turns out that it does. These high energy particles, when they strike the upper atmosphere, it's like shooting a bullet into a box of marbles. All kinds of shards would go out. And what happens is that these particles actually cause nuclear transformations in isotopes in the atmosphere. Carbon-12 is changed into carbon-14. Beryllium-9 is changed into beryllium-10, and chlorine-35 is changed into chlorine-36. All of these cosmogenic isotopes, they're made by radiation striking the Earth's atmosphere. Most often, this happens because of cosmic rays, things that happen, events outside our galaxy producing cosmic rays. The cosmic rays make kind of a steady background level of these cosmogenic isotopes. But when we have a big solar storm, we get a big spike. And carbon-14 decays in about 5,700 years, beryllium-10 about 1.4 million years, and chlorine-36 takes about 300,000 years. And we take a look at this, and we can now go ahead and take ice cores. We have ice cores that go down a kilometer or more in Greenland and in Antarctica. And we find that, we can track in the layers, we can track the relative abundances of these cosmogenic isotopes. And when we see a big spike, you know, especially if you're talking 5, 10, 20,000 years ago, that's not technology, friends. That's the sun has done that for you. And so Antarctica and Greenland provide us about 800,000 years of viable records with these isotopes. And so we see there was a big spike in isotope production that dates to 9,198 years ago. That seems incredibly specific, but indeed their data is that good. They can track it to a single year. And so in the year 7176 BC, that's what, 35 centuries before the first Egyptians laid a stone for the pyramid.
Jeez. Before
the ancient Greeks, the ancient Chinese, you're talking maybe the Aborigines in Australia were keeping records that far back. Six-fold increase in chlorine-36. They think this event was at least 10 times more powerful than the Carrington event. So, and at that time, it didn't harm anything. It wasn't a danger to any of the life on Earth. because nobody had wires or electronic equipment or even basic electric circuitry. It just didn't exist at that time. There would have been this tremendous auroral display, but
No electronics in the fossil record back then.
no electronics in the fossil record. And so the interesting thing, they tracked this back and they followed the 11-year solar cycle. Most of our big coronal mass ejections occur during solar maximum, but these bad boys seem to occur during solar minimum. The sun is quiet and then boom, huge detonation. There was a Carrington type event in 1903. And when's the next one? 1859 to 1903 is about 40 some years, and it's been 115 or so since the 1903 event. And so you go, wow, or 110, I guess. Anyway, so you look at this and you go, wow, that's a long time. And wow, are we due? We just don't know. We have no information about how these things work, or are they on cycles, or are they essentially random? Was it because a giant asteroid hit the, we have no idea. Did a giant asteroid hit the sun, cause a huge explosion? We don't know. One of the ways we're trying to find out is we have the Parker Solar Probe, which is going to be next week's How Do You Know? We're going to talk about the Parker Solar Probe. We have so many great space observatories around now that are just amazing. And we're going to talk about the Parker Solar Probe. For those of you that like these sorts of things, I've given you links for articles about solar flares, solar prominences, the Carrington Event, and the solar tsunami, and some accessible things, and then why we hate changing clocks, and a link for the interesting idea about supermassive black holes forming from dark matter. So all of those things are in the link, friends. And Scott, we also have a special announcement for today, and happy to share that with all our all our viewers.
You have a new book, right?
I do. I have a new book, and it's very exciting. Star Mentor.
I'll run the little promo video for it here.
You got the little promo? There it is. I love this, by the way. Thank you. There you go. Hands-on projects and lessons in observational astronomy for beginners. And Scott had a role in making this book come true and making it possible. Scott was very encouraging about writing this book, and I started over a year ago. And the reason for this book, the pandemic. We have millions of new telescope and binocular owners because of the pandemic. People wanted something they could do in the backyard. Astronomy offered a fun, interesting hobby. And Scott will tell you that sales of telescopes and binoculars, optical instruments of all kinds, went 400 to 500%, 4 to 5 times the normal rate. And people ordering new equipment experienced significant delays because there was such a huge demand. Well, the other thing is people were working in their backyard. The astronomy club system essentially got shut down by the pandemic. People weren't going to astronomy clubs. Astronomy clubs weren't having personal meetings. And the traditional thing, Scott, as you know well, for someone who's new to the hobby, who has a brand new shiny telescope, go find an astronomy club and say, oh, I have the Wonder Sky 2000 Miracle Edition. And they bring their usually modest new telescope, which is new and shiny and big to them. And people at the club go, wow, that's great. Let's show you how to use this. Let's show you how to read a star map. Let's show you how to find Saturn and Venus, and how to start looking for galaxies, and how to learn constellations. All of this help. This whole social support network was just gone. Yeah. So we have these millions of new people. We also have lots of people who are experienced astronomers who are not experienced educators. We have people, and Scott, you know these folks, I know these folks, people who are absolutely brilliant at what they do, but they couldn't explain it to another human being for the life of them.
That's
have,
true. That's true.
yes, and that's far more common than you might think, friends. People, and you may have experienced this yourself. If you have a telescope and someone's come up to you and said, ooh, you have a telescope. And as soon as you set up a telescope, it's a party in a box. You are now seen as the one who knows stuff, and people want to ask you questions. The questions just come bubbling out. And how do you help them? Someone says, oh, you have a telescope, I have a brand new one. I can't figure out how to put it together. I want to use it with my kids. And will you help me? Star Mentor is written for you too. It's designed to help people who already have equipment learn how to teach and guide others. And for millions of people who have no Star Mentor, they have no access to someone.
Right.
Then
One of the things
Star
that
Mentor
was good though
is a
about
guide
this
for
whole pandemic is that in the vacuum of not being able to go to a club meeting or go to a
Right.
Star party, many organizations turn to social media,
Yes.
Zoom,
Yes.
and being able to broadcast. And those are the three things that we worked on here at
Yes.
Explore Scientific, and we created the Global Star Party. And we work closely with the Astronomical League to help them
Absolutely.
do outreach to their members. Their membership
Absolutely.
grew during that time by over 3,000 members, and
That's astounding.
which is great. So and
astounding.
it's still growing. So
And it should.
but I think this year we're going to start to see some in real life, in real person types of star parties.
Yes.
We have some planned, which would include the Starmus event. It would include the Nebraska Star Party. It might include the Cherry Springs Star Party, which is, I think, in July, something like that. So as we get into summertime, we're
Yes.
hoping that COVID is not as big of a problem as it was. And
Indeed.
hopefully that fuel costs have not risen to the point of where you can't afford to drive to one. Okay.
Right.
So that is
Right.
that is another issue that we're facing today. But nevertheless, I think even as these in real life and real person types of events are reestablished, they will be mixed with being online at the same time. So there'll be hybrid events, and that's what we plan
Right.
to do as well.
I'm going to an event at the River Ridge Star Party, August or April. No, it's March 26th. It's coming up here in about a week, and that's down in the Momel area in central Arkansas, the Lake Dardanelle. So this is my first actual Star Party in about 2 years. That's actually being done in person. So I'm very excited. And I enjoy observing on my own, but I really love going to Star parties and taking my equipment and meeting new people and having people come up and go, wow, is that yours? Can I have a go? And sure, what am I looking at? And the whole Star Mentor experience for me is I've missed it.
It's very important for people like you that do outreach. I know.
Yes.
There was some comments here as
Sure.
as you gave your talk. Let's see. Martin Eastburn points out that different particles are absorbed in different shields. Back in physics research in school, we had to stack up lead, cement, and paraffin in an igloo. Neutrons are stopped in paraffin were stopped in paraffin detectors there.
Yes.
Okay.
Yes.
Let's see.
Basically, alpha particles, very low penetration. A sheet of paper will stop them. Beta particles, you need a thin sheet of metal like tinfoil will stop them, or about 5 or 6 inches of plastic or dirt. And then gamma is very penetrating. You need many feet of lead to stop them. And neutrons are different. You're not getting many neutrons from a solar flare event. Those are stopped in the upper atmosphere. We don't really get a lot of particles reaching the ground from a solar flare event. Most of that impacts the magnetosphere. The magnetosphere makes life possible here. Solar flares would absolutely, without the magnetic field, would absolutely roast the surface and destroy biological molecules. It would be a holocaust, quite literally. And the magnetosphere protects us. That's one of the reasons we think if we're going to find life on Mars, it's probably going to be deeper underneath the surface, because Mars has no more magnetosphere. Its core solidified, stopped, and the magnetic field died about 3.5 billion years ago. And so, yes, our viewer is absolutely correct. Different particles require different kinds of shielding. And if you're in a space station, that's going to be important to you. If you're on Earth, the magnetosphere protects you, and you don't have to worry about that.
Yeah,
so
you already have your force field, so.
you do.
You
It is quite literally a Star Trek, Star Wars style force field. It really is.
Chris Larson says the Carrington event, if it happened today, would shut down the world.
Yeah, that would change the path of our civilization. Old people would suddenly become important because we know how to do stuff without cell phones and YouTube. And
Right.
you think about all the computer aided manufacturing. Think about just our industry with telescopes and binoculars. Nobody makes
Sure.
these things by hand anymore. Cave instruments back in the 50s, the mirrors were ground by hand, which is why telescopes weren't very big and they were terrifically expensive. And nowadays, this is all computer aided manufacturing, and you wouldn't have that. You wouldn't have that. The supply of so many things that are made by computer manufacturing. All of our modern automobiles, your 1950 classic.
Self-driving Tesla would
Those
stop
are all dead.
driving.
All your electric cars would be dead. Most of your modern cars. My wife has a new car this year. She was able to purchase one, and it has the technology in it is just stunning. And it would all be fried. It would all be fried like bacon.
Right.
And I'm not sure my car's a 2017. I'm not sure either of our cars would start. Probably my Slingshot would. It's
Quite
much
a few
more.
computers in cars anymore.
Yeah.
Jim Zastra says back in March of 1989, we had a partial blackout due to a solar flare.
That's correct. That's correct. We did. And the ESA, I think it was the Beagle probe. I forgive me if I'm wrong, folks, but I know the ESA lost a probe because there was a huge solar flare that fried their probe just a few days before it reached Mars. And they lost the whole mission. It was very sad. But yeah, you mean Mars is not far enough away to be safe
No.
from an event like this.
Josh Kovac, watching on YouTube, asks, could something like that produce enough energy to alter Earth's orbit?
No, it would not. If you think about all the material from a coronal mass ejection, let's say it was 1,000 gigatons, which would be a teraton. The Earth is 10 to the 26 kilograms. And so it would literally be like throwing a marshmallow at a charging rhinoceros. It's just not enough mass to affect the massive physical body of the Earth. On the other hand, it's going to play merry hell with the magnetosphere. It's going to give it a big punch. It's going to vibrate and oscillate for a long time. It would be very much like dropping a cannonball from a skyscraper onto a trampoline. The trampoline, even if the cannonball bounced off, would continue to vibrate for a very long time. And all of those vibrations produce radiation, radio waves, and inductions in metal objects. And that, it's like hitting a drum. You see the energy would decay over time, and it would be much the same with the magnetosphere. And yes, a Carrington type event would change the path of civilization. We really would default to local government. We wouldn't be able to federally govern anything over any country-sized area anymore. And it would take, a lot of people would die simply because with modern trucking, rail, and air and sea navigation, even if you had diesel ships at sea bringing cargo, their navigation would be knocked out. If you had trains, old locomotives, which are diesel, certainly modern trucks with the chips in them, they would be knocked out.
Medical life support would be knocked out.
Oh, medical life support. Yeah. But just if you talk about a big city like New York or Chicago, and trucks are knocked out, so food supplies stop getting there, you would have a famine. The death toll in the month after a Carrington type event would be terrific. It would be absolutely terrific. And a great section of our social fabric would be destroyed and have to be rebuilt. It would be quite the dystopian scenario.
Right. Chris Larson says, I have a close relative that is very involved in a large state's Office of Emergency Services. This, I guess he's talking about a type of Carrington event. This is high on their list of threats. Are you aware, Daniel, of protocols that go into place in case of something like this?
I am not. I'm sure that they're there. Mm-hmm. I'm not certain that they aren't whistling as we walk past the graveyard, sort of stuff. We can plan all we want to, but it's like having a plan for a tornado. Okay, it's like having a plan for a tornado. There's a tornado warning, and we go down into the basement, and we have a 5-gallon jug of water and batteries for our flashlight. And if the tornado goes through our town and our house is relatively intact, even if it's damaged, our tornado plan is probably satisfactory. If we get a bullseye hit from an F5, our plan is now worthless because the devastation had just exceeded our ability to plan and respond. And it's like the Fukushima nuclear plant. They had a plan. Up to a magnitude 8 earthquake. And you think, holy crap, that's like destroyed San Francisco type earthquake. And they got a 9. And nature is simply capable of overwhelming our ability to plan. I'm sure there are plans, and it's good to have plans. We should have plans. It's the DART mission. We're planning to deflect an asteroid. Right. We had a show on this, on Pal El Haram, and how it was destroyed by an asteroid strike. A city 40 miles away, Jericho, the blast from the event knocked the walls down. The Dead Sea salt water was sucked up and deposited over a large area, made it unfarmable for 6 centuries. A Carrington event would destroy an awful lot of the fabric of our society. We do not, in the 1960s, we still governed mostly by telephone. News was by newspaper, and after the 1960s, we became more and more dependent upon our electronics. Today, we're virtually totally dependent upon them. A Carrington event in 1950 would have been bad, but we would have recovered quite quickly. Today in 2022, it would take us a decade, and life would never be the same post-apocalypse for those that survived. And Earth's population would take a large hit simply because billions of us depend upon our technology to bring in food, clean water, medical essentials, anybody who's vulnerable because of special diet, medical needs, you're gonna perish. Because, if you're dependent upon insulin and transportation shuts down, if you're dependent upon heart medicine, transportation shuts down. You need regular medical care to survive because you're a heart patient or a cancer patient, and these systems shut down. You have a heart attack and you can't dial 911 and you can't get an ambulance to come pick you up. You're probably going to die. If you're in a major metropolitan area, and you look at the political map, this would impact people disproportionately in blue cities and not rural red areas. And we're talking politics, it would be a differential impact. Simply because of where people choose to live. If you live in a major city, if you have a Carrington event, you need to start to leave, and you need to leave right now. And you need to not be picky about what you grab. You grab your kids, and if you've got a bicycles, that's great. And you get the heck out of Dodge, because it's going to become carnage in a major city. It would be a disaster.
Let's see. Jane Powell Hurley says, I've got to go back and listen again. I've been wondering about all of this, especially how it will impact my industry. I can't wait to find out what a solar tsunami is. I know what a silver tsunami is. Okay. All right. Let's see.
And just to clarify for everybody, Scott, we're not talking a tsunami. Solar tsunami is not a technical scientific term. It's just a metaphor for an overwhelming release of energy and power from nature that overwhelms human defenses and planning, much like a tsunami. We've all seen these videos on YouTube, I'm sure, where the water just comes in and sweeps away buildings and roads and cars. And it's just so much water, so much force in a very short amount of time. A solar tsunami would be much the same. This devastating amount of energy strikes the earth, and we can't block it. Nothing we can do about it. We simply have to pick up the pieces and move on afterwards.
Right. Someone asked, what causes sunspots? And another person answered, Chris Larson answered, I thought they were generally formed by the geomagnetic disturbances finding their way to the surface, the quote unquote surface of the sun.
It's solar magnetic. It's areas where the magnetic field is concentrated. Where the magnetic field is concentrated, it allows these field lines serve as transportation conduits for energy out of the corona and the photosphere, rather, to the corona. And so this energy from the photosphere has a conduit so it can flow out. It's like poking a hole in one of these soft-sided pools. You give a place for the water to come out. And so the solar field allows more energy to be released. And so the photosphere cools off. But that's really a symptom. That's really the sunspot that we see is just a symptom of the magnetic disturbance that's happening in the sun's corona. And the magnetic disturbance penetrates deep into the interior of the sun and far out into the corona. So the magnetosphere, the sun is not solid, it's plasma. Plasma is conductive of electromagnetic energy. And so the sun's magnetosphere penetrates and extends beyond what we see as the surface of the sun. It really is, co-inhabits the same space. And the sun is really, it's not just a fusion explosion. It's not just a ball of plasma. It's also a great ball of magnetic energy. And all of these things co-inhabit the same space. It's what makes solar physics so much fun and so interesting and complex. And the differential layers rotate at different speeds, and those twist and distort the field lines. And it's just like stretching a rubber band. You're putting energy into it. When these field lines are stretched and distorted by the differential rotation of various layers of the sun, and not just laterally, but concentric shells of different material moving in different ways inside the sun. Wow, you get a lot of magnetic stuff, and every once in a while something gets twisted up and it snaps. It's much like an ice dam on a river in the winter, and when the ice dam breaks, and then everything behind it flows down very suddenly. It's the storage and release of energy for tectonic plates. They grind past each other, and they're storing up elastic energy in the rocks, and then suddenly you get this slip. Tremendous amounts of energy are released in a seismic event. It's much the same. This punctuated equilibrium model is common throughout nature. And the sun has it too. And there's a lot of talk about, oh, we should harden our electric grid. We have a hard enough time maintaining it. Hardening it would cost trillions of dollars. It would be a mega project akin to the Egyptians building the pyramids. And the devil of it is, do you go ahead and harden the electrical grid, etc.? Do you spend the trillions? How are you going to sell that to the average populace? Oh, we need to take money away from widows and orphans and military defense and all of these things, subsidies and all of these things that the government funds. And we're going to harden the electrical grid just in case. And somebody's going to say, but what if it doesn't happen? Right? It's like buying a fire extinguisher or a burglar alarm, except much more expensive. If you buy a burglar alarm and you don't get broken into, or you have a fire alarm and your house doesn't burn down, okay, I spent a couple $100 on a fire alarm and my house didn't burn down, and that's fine. I don't worry about it. If somebody said, oh, let's spend $150,000 on putting a fire protection system in your house, and you're like, holy crap, that would take me 30 years to pay for. Right. How would I do that on my, $30,000, $40,000, $50,000 a year salary? It would be like another mortgage. How could I afford that? I couldn't send my kids to college. I couldn't buy gasoline to go to my job. I couldn't pay for my kids to get, an education. Right. It's such a terrific expense, and people see it. It's far beyond most people's experience. Solar auroras, Aurora borealis, that's so pretty. We don't realize the amount of energy it's like saying, ooh, mushroom cloud, pretty. We don't realize what we're grinning at.
Right.
We are happy little naked apes, and we don't understand what we're grinning at. Asteroid defense is a little easier to sell because Tunguska, because the Chelyabinsk event in Moscow, or outside of Moscow, or I guess it was in Siberia, 2013, the Chelyabinsk meteor. And we can say, oh yeah, we see what happens. Barringer crater, yeah, that's a hell of an impressive hole in the ground. So the Breedfort ring and all of those places, and we go, yeah, okay, that would be really bad. And we can take a telescope and we can see the rocks out there, and we can track them. And we have bulletins. Oh, this rock is coming in between the Earth and the Moon this week, and we see these things, and we go, wow, okay. But the solar storm, we can't see the rocks in space, so to speak. We have no idea how the darn thing works.
Yeah,
we have no idea really of the mechanisms that lead to this tremendous buildup of energy. We don't know what the warning signs would be. We can't even say, holy crap, we're going to have a huge magnetic storm. Let's take all our satellites in safe mode and unplug all your electronics and all of that. It's going to be here in 48 to 72 hours, and the world exists somehow without Twitch, Twitter, YouTube, and Facebook for a few days. And then the solar storm hits and we go back to normal. We don't even have a model to predict. We can't do like we do with hurricanes and say, oh my God, here's this storm forming in the Atlantic. Batten the hatches, here it comes. We don't even have that much information. So.
Daniel, you wrote several books with Maurice as the central character,
yes.
Science fiction books. Harold Locke has read all of them.
Wow.
And he's wondering when book 4 of Maurice comes out.
Harold needs to send me an email. As you know, Scott, I am wrestling with the publisher of the Maurice series. There is a book 4 called Revolt in Volkov Crater. And I would be happy to send Harold a complimentary PDF copy of the next book with my compliments. He needs to send me an email at astronomyforeducators@gmail.com. And I will feed the need for Maurice. That is the 4th book. I have planned and thought about others, but I haven't written them. Star Mentor was my big project in the last year. Maurice books are easier to write, and I have the fifth book in the series would be Terror at the Lagrange Point Station, and that builds on Buzz Aldrin's concept of the cycler, the spacecraft that goes between the Earth and Moon and Earth and Mars and never stops. It simply it's like one of these trains that circles the airport and just takes people on and lets people off. Right. It's kind of like that. And there's another book, sixth in the series would be Children of the Ring, which takes us out to the ice mines of Saturn and various other places. So there are more books planned in the series, but I haven't written them yet. And hopefully someday I'll get a new more legit publisher for that series. It'll be reissued, and we'll do some more on that. But gosh, thank you. I'm so glad to hear that you've enjoyed the Maurice books. I had an awful lot of fun writing them. They're lots of fun.
Well, great. Well, Daniel, thank you very much. And for those of you who love learning more about Daniel Barth and all of his courses, he's heading up on number 38 next Monday. And so, but you can go to explorescientific.com, the How Do You Know page, and I will post that right now on.
And for folks who are thinking about Star Mentor, my latest book, that will be released sometime in late May. So if you're going to go look for it on Amazon or your favorite retailer right now, it has in production, and all the final edits have been done. The illustrations have been set and the cover's been set and all of that. But printing and production schedules being what they are, it's going to come out in about 2 months now. So sometime in late May, and as soon as it's available, I will, Scott and I will let you know. And we'll have to give away a couple of signed copies.
Nice. When
we get to an episode sometime this summer. So I'm really hoping people will enjoy it. I'm hoping it will be a popular and fun book and of value to people. It's kind of like coming along with me and doing an entire observational astronomy course with me, because I drew material from all my teaching resources over many, many, many years for that.
That's
book.
Great. There's a comment here written in another language. The question is, I've seen, or the comment is, I've seen videos of particles that have collided with the sun, and it seems they are the ones that have generated the explosions that are seen.
There's some indication that a large asteroid striking the sun could cause some sort of an eruption. But we know that solar flares and solar prominences and all these sorts of things occur without any impact to trigger them. It's been a staple of science fiction for years that if you were conducting interstellar warfare with a galactic civilization, you could just go and drop a big asteroid into somebody's sun and cause a big solar eruption, which would devastate the planets where there was life. And so the space marine tactic, drop an asteroid, the solar magnetic storm destroys their civilization, and then you go in and you can easily conquer their planet because they've all been knocked from space age back to the Stone Age by this magnetic tremendous event, the magnetic storm. So that's kind of a staple of sci-fi. If any of you out there are thinking of doing it,
please don't. Just give up. Don't, please.
Nobody has the technology for that. No, we can send a spacecraft out and we can swat an asteroid, but we don't have the technology to go and capture an asteroid and move it. We couldn't take even like an asteroid Bennu and go and shove it into the sun. We don't have that technology, and we are many decades away from it. That won't be a threat that Scott or I have to live with. Maybe our great grandkids. I don't know.
Right. Okay.
there you go.
All right. Well, have a great evening. And we'll
Thank you,
be back
everybody.
tomorrow with Global Star Party, our 86th event, co-hosted by Maxi Falaris. So until then, take care, and we will see you later.
Clear skies, everybody.